Hello, Kiskers. My name is Kyung-hoon, and today I will tell you about IBM Quantum Spring Challenge Lab 4. Brief introduction to me. I'm Kiski Audible Cat, and I mainly participated on Kiski Matter and some community events like this Quantum Challenge. I did my undergrad at Seoul National University, majoring in physics and computational science, and my most research works are about semiconductor quantum dot qubit and diamond coral center qubit. I'm now doing PhD in Duke University and majoring in physics, and I'm now researching about ion trap quantum computing. So about lab 4 is about error correction, right? So before we discuss about error correction, we have to first discuss about the error. And also before discussing about quantum error correction, we will discuss about classical error correction first. So in computer, we use binary numbers, right? So we store some numbers in 0 or 1. Bit flip error is unwanted bit flip from 0 to 1 or from 1 to 0. But it's very small change, right? Is this kind of error significant? The answer is yes. Let's see this example. So in 8-bit computer, we can store the number 1 as a 00000001, right? Let's imagine we have single bit flip error in the first bit. Then the bit look like 1000 and 0001. And this is 129. So it's a huge difference. So we definitely have to care about this kind of bit flip errors. So how can people correct this kind of errors in classical computer? So let's assume that we have a single bit, which have the number 0. First, we can copy the bit several times. Let's use 3 for the example. And then let's assume we have single bit flip error in the middle bit. And we can do majority vote on these bits. And so we have 2 0 and single 1. So we know that this bit is originally 0 and the 1 is error. So we can correct that 1 into 0. Finally, we can restore the original bit. Let's tell you about some terms first. So we made single bit to 3 repeated bits. We call this kind of process as encoding. And finally, we restore this 0 bit, and this restoring process is called decoding. So in summary, we use 4 steps to correct the errors. First, encoding. Second, detection. Third, correction. And finally, decoding. So is this method works always? The answer is sadly no. Let's see this example. So let's imagine the case with 2-bit flip error. So we can encode the single 0 into 000. And if we have 2 flips, then we have 101. So in majority vote, we decide the error is 0. So we correct 0 into 1. And after decoding, we get the bit 1. So this does not work. We can calculate the probability of how this error correction method works with basic math. So probability of no flip is 1 minus p power of 3, and probability of 1 flip is 3p 1 minus p cube squared. So if you add these two numbers, then you can calculate the success probability. And on the other hand, you can also calculate failure probability by adding probability of 2 flip and probability of 3 flip. But these equations doesn't intuitive, so I draw a graph. So x-axis here is bit flip probability, and y-axis here is majority vote failure probability. This axes are in log scale, so this increase is actually more huge than you see. On the other hand, if you repeat the bit more and more times, you can actually reduce the failure probability as shown in this graph. So in exercise 1, you will write your own encoder and decoder for this kind of classical repetition code. And through this exercise, I hope you can be familiarized with the concept of bit flip error, repetition code and majority vote algorithm, and encoder and decoder in error correction algorithm, and finally, success probability of error correction algorithm. So the sad news is that qubit is also not perfect. Actually, and it contains more error than classical bits. So we definitely need error correction method for classical case too. Can we use the classical error correction algorithm into our quantum error correction case too? The answer is also no. Why? First, we cannot copy the qubit state. This is known as no cloning theorem. And second, we cannot directly measure the qubit state without collapse. So we cannot detect the errors just simply directly measuring the qubit states. So we have to find some another way to correct the errors. So I told you that error correction algorithm have 4 steps: encoding and detecting, correcting, and decoding. So let's look the encoding process first. So let's imagine we have single qubit with some arbitrary state, which can be written as alpha 0 plus beta 1. And because of the no cloning theorem, we cannot make precise state, right? So instead, we can make this alpha 000 plus beta 111 state. The remarkable point is that this precise 3 is different with this repeated precise state. We can make this state with below encoder. So originally we have alpha 000 plus beta 100 state. And after this CNAT gate, the first term does not affect because the first qubit have 0 state, and second term affected because the first qubit in second term state is 1. So now we have alpha 000 plus beta 110 state. And finally, after one more CNAT gate, we can get alpha 000 plus beta 111, which is precise 3. And we can do same thing for decoding. So if we apply 2 CNAT gate, we can restore this alpha 000 plus beta 111 state into alpha 000 plus beta 100 state. So now we can do encoding and decoding. So the remaining thing is detecting and correcting. Before look about this detecting and correcting, let's see the bit flip error on qubit first. So what is bit flip error in qubit state? So if we assume that single bit flip error on the first qubit, then it is same as applying XII gate on the qubit state. So alpha 000 plus beta 111 state will be changed into alpha 100 plus beta 011 state. In same way, if we have bit flip error on second qubit, the error can be written as IXI, and the final state will be alpha 010 plus beta 101. And finally, if we have bit flip error on third qubit, then the error is IIX gate, and the final state will be alpha 001 plus beta 110. So how can we detect this kind of errors? As I told you, we cannot directly measure each qubit. So we have to use some another way. In this correcting method, we will tell you about the method using some unselect qubits. So let's imagine we have 2 CNAT gate from encoding qubit 1 and encoding qubit 2 to unselect qubit 1, and also to another CNAT gate from encoding qubit 2 and encoding qubit 3 to unselect qubit 2. Then after this 4 CNAT gate, our final state will be changed from the left-hand side to right-hand side. The first row means that we have is about the case we have single bit flip error on first qubit, and second row is about we have single bit flip error on second qubit, and last row is about we have single bit flip error on the third qubit. We have there's 2 noticeable points in this result. So first one is that encoding qubits and unselect qubits are perfectly unentangled after this operation. if you see left-hand side and right-hand side each, the unselect qubit states and uh, uh, encoding qubit states are in the product state, which means that there is no entanglement between these two qubits. So, which means that measuring unselect qubits do not affect on the encoded state. So we can measure the unselect qubit and extract some information from them without destructing the original encoded qubits. And second remarkable point is that unselect states are distinguishable about different errors. So let's think about the no error case first. If there's no error, unselect qubit definitely have 0, 0 state, right? And if we have single bit flip error on the first qubit, then unselect qubit state is 1, 0. And if we have single bit flip error on the second qubit, then the unselect qubit state is 1, 1. And finally, if we have single bit flip error on the last third qubit, then the unselect qubit state is 0, 1. So we can distinguish, we can find which qubit have error only by measuring the unselect qubits. This kind of measurement is called syndrome measurement. Sadly, the circuit I provided, for example, is not the answer for our exercise 2, but it's very similar. You have to make your own syndrome measurement result, which satisfies the below condition. If you look here, they require you to write the circuit which have the 0, 1 unselect state when the error occurred in first qubit, and 1, 0 for the error occurred in second qubit, and 1, 1 error occurred in the third qubit. But in my example, if you have a single bit flip error in the first qubit, then it's 1, 0. And if you have single bit flip on second qubit, then it's 1, 1. And finally, for the single bit flip on the last qubit, then the unselect qubit state is 0, 1. So it's different with this example. So you have to write your own code and check whether your unselect qubit have this kind of final states. Finally, for error correction, based on syndrome measurement research, you can find that you can decide which qubit have error, right? So you can now correct that by simply flip that error qubit. You can now correct that error. You can do this by see if syntax in Qiskit, and I think you're already familiar with this syntax because I guess that you already solved the previous lab examples. This kind of syndrome measurement method is one of the most basic error correction methods. So if you're interested in quantum error correction, I hope you study these further keywords. Thanks for the listening and enjoy your challenge. Goodbye.